In this lecture, I'll talk about inverse Laplace transform. So in the previous two lectures, I talk about the property of Laplace transform. So in this lecture, I'll talk about the inverse Laplace transform. So before getting started, let's talk about what is the definition of the inverse Laplace transform. So inverse Laplace transform is defined as this. So we basically talk about how do I convert from I try to give a fs in the S domain, capital Fs. I want to try to figure out the corresponding ft, the little ft, okay, in the time domain. Okay, as we know, the Laplace transform is try to, so if I give ft, so this Laplace transform is given by integration from 0 to infinity, okay, e minus st, ft, and dt. So that's the definition of Laplace transform. So inverse Laplace transform is given by ft, which is L inverse of fs. The definition is a little bit complex. Okay, the definition says, which is given by 1 divided by 2 pi times I. Okay, so the I is, so here I is square root of -1. And the limit of when t goes to infinity, gamma of gamma minus I times t to gamma plus I time t, and est fs ds. Okay, so this gamma is a real part of s. Okay, so this is the definition of the inverse Laplace transform. So actually we don't need to use, so even if I have definition, so all of the following computation we don't have to remember. You don't have to remember this. We never use this definition to compute the inverse Laplace transform because it's really complex. To speak of the property of inverse Laplace transform, so there are a couple of properties for the inverse Laplace transform, mainly two of them. The first one is the linear property. Basically what it says is L inverse of f1s plus f2s is just the inverse Laplace transform of individual function f1t and f1s and f2s is the sum of this. And also we have homogeneity property, which says you can scale it your function fs by alpha, which is the same as alpha times the L inverse of fs. So you can put the scalar outside. Okay, that's the two main property we have for the inverse Laplace transform. Okay. So okay, since I mentioned before that we don't use a definition to compute the inverse Laplace transform. So what is the main approach we use to compute the inverse Laplace transform? So the key techniques that I'll talk about in this lecture and also the next lecture, talk about the key technique, which is called partial fraction expansion or partial fraction decomposition. Okay, that's the same. It means the same. Okay, so now I'll focus on talking about what is this partial fraction expansion or partial fractional decomposition technique. Okay, before talking about that, I will give a few definitions and some kind of property we mentioned before talking about how we really use this partial fraction decomposition approach. So basically speaking, if I talk about the transfer function, the function fs and the gs, so typically we are talking about, okay, we're talking about this fs, okay, over here. What typically we talk about when we talk about inverse Laplace transform, we talk about something like fs divided by g sub s instead of direct talking about the fs. So you sort of can see a generic fs function. We typically talk about the inverse given this form. So it's given by fs. You also call it numerator. So this is just polynomial. And g sub s, this is also polynomial. So you can say like we're talking about the inverse Laplace transform for a fraction, which is a polynomial divided a polynomial. So it's polynomial of s divided another polynomial of s. So this is what the typical form we will need to find out for the inverse Laplace transform. Okay, now let's speak about the fn and the gs. So first of all, we mainly talk about the case when the degree of fs is less than degree of gs. Okay, I'll give example talking about what is the definition of degree. Okay, so assuming this is the case, And also assuming my g sub s, okay, the denominator is written as g1s times g2s. So these g1, g2s, they all g1s and g2s, they are all also polynomials, and also g2s. This is also polynomial. Okay, so if that's the case, I can write the partial fraction decomposition says I can write fs divided by gs, of course, which is the same as fs divided by g1s times g2s, because the gs is the same as g1 as g2s according to this property. So which is actually we can decompose this as f1s divided by g1s plus f2s divided by g2s. So also we have the property is degree of f1s is less than degree of g1s, degree of f2s is less than degree of g2s. This is the main idea of the what is the partial fraction decomposition says. Okay, so you can decouple in this way. Now let's talk about an example. Okay, let's say what if I have g sub f of s is s plus 1 and gs is s plus 1 s plus 2 times s plus 3. Okay, so if I go back over here, okay, it says we haven't talked about degree. Now let's talk about what is the degree. Okay, the degree of fs, also degree of gs, degree of fs and g sub s is the highest power of s when the coefficient is non-zero. For example, here the fs, the degree of fs is the highest power of s with non-zero coefficients. So here is, you can see is 1 times s0, you can consider this way. This is s1, s to the power of 1. So the max highest power of s is just 1. So this degree is 1. For this guy, okay, I don't know the degree yet, but I can write this one as, we can do the computation, is s squared plus 5s plus 6. So the highest degree for this guy is, because the highest power with non-zero coefficient is 2, right? So this is 2. So I have degree of, so this is, which means this is less than this. So it satisfies the property I mentioned over here. And also I have gs can be written as g1s and g2s. You can sort of see this is my g1s. This is g1s. This is my g2s. Okay. So according to the partial fraction expansion or decomposition, I can write fs divided by gs as s plus 1, something divided by s plus 1. Because remember here the degree of f1, whatever, this is f1, this is basically f1, this is f2, right? So this is my g1 s, this is my g2s. So the degree of f1s must be less than degree of g1s. So degree of this g1s is 1, because the highest power is 1. Degree of g2s is also 1. Less than that, it must be 0. Degree of 1s must be 0, right? 0 means it's a constant, okay? And so also f2 has to be a constant, because degree is also 0. Okay, so that means I have two constants over here. So which means fs divided by gs over here is given by a, it can be decomposed as a divided by s plus 2 plus b divided by s plus 3. So here a and b, they are constant. Okay, the reason we do the decomposition, because individually this one, according to the property over here, the linear property over here, so if I want to compute the inverse of this guy, if I want to compute the inverse of this guy, okay, it's the same as the inverse individually. Apparently individually this guy is easy to figure out, okay? I'll talk about example later on why it's quite easy to figure out the individual component over here. Okay? Alright, so that's the basic idea how to do that. I haven't talked about how to compute this. This is what is the partial fraction expansion or decomposition means. Okay, so the basic idea is I want to sort of reduce the polynomial, higher order polynomial into a lower order polynomial, and it's easy to figure out its inverse Laplace transform. Okay. Alright, so the key idea is, I talk about how to do it, I haven't talked about how to figure out A and B. The key idea is I don't know how to figure out A and B, right? If I figure out A and B, I'm done, right? Because I don't know how to do A and B. Now let's talk about how do I determine this F1s, F2s, etc. Meaning, for example, how do I figure out A and how do I figure out the B? Okay. Alright, so in the previous example, let's talk about an example over here. Let's say, what if I have fs over g, this fs, I want to find the inverse Laplace, which is given by s plus 2 divided by s plus 1 time s plus 3. Okay, so I want to write this into as, according to the partial fraction expansion or decomposition, it means that I can write this one into s plus 1, s plus 2, because you can see this is gs, this is g1s, g2s. Okay, you can write this one, and also the degree of s plus 3, the denominator, numerator is 1, the degree of s plus 1, s plus 2, which is 2, because this guy is s squared plus 3s plus 2, so the highest power of s is 2 with non-zero coefficient. Okay, so it satisfies partial-dimensional decomposition. So this one can be written as a divided by s plus 1 plus b divided by s plus 2. Okay, alright, and the reason here is constant because the degree of the numerator has to be smaller than the degree of the denominator, and the denominator always has degree equal to 1, so the degree of numerator has to be 0, which means that it must be constant. Okay, alright, so how do I figure the a and b? What is a, what is b, right? Straightforward way is, well, what I have to do is I just say I have a and b over here. Then of course this guy, this side and this side, they must be equal because this guy equal to this guy, right? Why don't we just assume I have some a and b? I try to figure out what a b value, right? So for the right hand side, I can try to match the left hand side in terms of denominator, and then the numerator should be the same, right? That's the main idea how we figure out the a and b value. So if I augmented this one, so I do this one, I multiply the first component over here. I multiply the numerator and denominator both by this s plus 2. So I get a times s plus 2 divided by s plus 1 times s plus 2. Okay. Similarly, for the second component, I'll multiply both the numerator and the denominator by s plus 1. So I get b times s plus 1 divided by s plus 1 and s plus 2. Then merge them together, I have s plus 1 and s plus 2 as is a denominator. And the numerator, I just do all the, put them together because I have a times s plus 2a plus b times s plus b. Okay, so I put them together as, this is s, so a plus b times s plus 2a plus b over here, and the denominator will be the same. Now because this must be equal, so the denominator, you can see those denominator, that's the same, which means the numerator must be equal, which means I have 1 times s plus 3, okay, must be equal to a plus b times s plus 2a plus b. Okay, this must be equal, which means the coefficient must be, because the coefficient for s is 1, and so it means a plus b must be equal to 1, and this constant value should be equal, which means the 3 must be equal to 2a plus b. Okay, once you figure out this one, you can figure out a is 2, b is negative 1. So which means I can apply here, the a is 2 and b is negative 1, which means I have here is 2s plus 1 plus 1 over s plus 2. Okay, so now we are finished the partial fraction expansion. Okay, now let's say if you want to figure out the inverse of that, L inverse s plus 3 over s plus 1 times s plus 2, which is according to the linear property I mentioned previously. So it's L inverse of 2s plus 1 plus L inverse, this has been negative 1, this has been negative 1 over here, negative 1 over s plus 2. Okay, so this is very easy to do because this guy is just, remember the L E minus T, okay, which is according to the property for the Laplace transform, this is 1 over s plus 1. Okay, so if you do the 2 twice of that, you get 2 over here, right, which is the same as this guy, right, which means if this guy means the same, which implies if I do the inverse, it means L inverse of 2 over s plus 1 has to be equal to 2 times e minus t. Okay, so which means this is 2 e minus t. This guy do the same thing, is just minus 1 times e minus 2t. Okay, this is very easy to figure out. Actually, the table for you to figure out this table, you can do the table inverse Laplace transform, use the table to figure out these two this 2. You don't actually have to do the computation like I do over here. Okay. Alright, this is why the partial fractional decomposition is very important to compute the inverse Laplace transform. Okay. Let's go over to the general case. Okay. Now the previous example I just talked about it. You only have G1 and G2. Actually, this can be expanded to a very general case. Okay. The general case. This is a general case. Okay. For the partial fractional expansion or decomposition. So if I give you the Fs and Gs, this is where I want to find the inverse Laplace transform. Assuming the degree of Fs is less than degree of Gs. This is the same way we compute the degree. It's the maximum power of S with non-zero coefficient. This is the definition of degree of a polynomial. So assuming here this is a polynomial, and this is also polynomial. Okay. And also I talk about the zero and the poles. Okay, the zeros is the solution to Fs being 0. So you set the denominator to be numerator to be 0, you find the solution. The solutions are called zeros. For example, if Fs is s plus 1 and s plus 2, okay, now you just set it to be 0. You have got two solutions. One is s is -1 and s is -2. So you have two zeros. Okay. Similarly, the poles when you solution to when you set the denominator to be 0. For example, if my g sub s is s plus 4 and s plus 5, okay, so your solution will be s is 0, s is -4, s is -5. So you have three poles. Okay, so that's how we define zero and poles for Fs over Gs. Okay. Another question is, what if the degree of Fs is not less than the degree of Gs? There's a way we can solve this as well. So this one I talk about very briefly. So what if the degree of Fs is greater than degree of Gs? I should write this one, degree of G sub s. Okay. If that's the case, for example, let's give me an example. If Fs is s squared plus s plus 1 and Gs is 2s squared plus s, okay, the degree, so you say degree of Fs is 2 because the maximum power for s with non-zero coefficient is 2. The degree of G sub s is also 2, right? The highest power is also 2. If that's the case, so what we can do, we can do Fs over Gs, right? So we can do some computation over here. So what I do here, I do 1/2 and 2s squared plus s. So this is, I basically want to cancel this term, okay, because this is, I want to get a lower order. So what I do is I do this denominator over here. So I put the same thing over here, but I put 1/2 because once I put 1/2, I get a 1 just s squared, right? And I have minus because you want to make sure that's equal to Fs. Minus the same thing, right? And then plus, this is plus Fs, right? It doesn't change because essentially these two will cancel out. The reason I'll keep this one over here, so 1/2 2s squared plus s divide this stuff, we'll get a 1/2 because this is just half of that. So it's 1/2 plus, okay, you can see the trick of what I'm doing over here. Once you do this over here, this remaining to be 1/2 of this 2s squared plus s. If you do the product of the individually, you get a minus s squared minus 1/2 s plus s squared plus s plus 1, okay? The reason I have this 1/2 because this will cancel out. You can see negative s squared and s squared will cancel out. The negative 1/2 s plus s, it becomes only 1/2 s. And the remaining one is still there. So it becomes 1/2 plus 1/2 s plus 1 divided by 2s squared plus s. So this one, okay, you can do it individually. So there's a table you can figure out. Let me do it over here. The reason this is a table, we can figure out, okay, you can find a table. This one, does go back to this one because this guy, even originally this Fs, the degree of Fs is not less than the degree of Gs, but by doing this trick, I can have this term, this guy is satisfied properly because the degree of the numerator is 1, degree of the denominator is 2, so it's satisfied properly. We just have to find the inverse according to what I said. The inverse Laplace transform for this guy is the inverse of individual according to linear property. Okay, L inverse 1/2 plus L inverse this guy, we can go back to the satisfy this property I mentioned over here. Okay. Alright, so we only focus on here when we assume that degree of fs is less than degree of gs. Okay. Alright, so there are a couple of ways, there are a couple of cases when we talk about try to find the inverse Laplace transform for fs over gs when the degree of fs is less than degree of g sub s. Okay. So the first case we talk about the case when we won't have distinct and real poles. Okay, what does it mean? This means I can always write a g sub s. This means I can always write a g sub s in s plus lambda 1 plus s plus lambda 2 so on until s plus lambda n. So here each lambda I, they are real because it has to be real, and lambda I is not equal to lambda j if I is not equal to j. So they're not repeated. We don't have the same poles. We have poles that are always different. Okay. So in this lecture, I want to talk about the first case. In the next video, I talk about two other cases. Okay. So first of all, let's start to give example showing how we do how we figure out the inverse Laplace transform. Okay. Assuming my fs is s squared plus 2s plus 1. Okay. And my g sub s is s plus 1 plus s plus 2 plus s plus 3. Okay. So when you check the poles, so the poles is when you set a g sub s to be 0. Okay, if you set a 0, you can poles are s equal to negative 1 and s equal to negative 2 and s equal to negative 3. So they are real, distinct, they're different. It satisfies the case 1, the property in case 1. Okay, so what it does is, if that's the case, we can always write fs over gs as each component is just each one we have. It's like each poles is s plus 1, s plus 2, s plus 3, and this is only the numerator is just a constant. They are all constant. Here they are all constant. So a general case says fs over gs is just a1 divided by s plus lambda 1 plus a2 divided by s plus lambda 2 plus an divided by s plus lambda n. So if this gs given by this form. So this is when we have distinct and real poles. So we can always write fs over gs as this, assuming my gs is s plus lambda 1, s plus lambda 2, so on and so forth, s plus lambda n. Don't remember that another condition is degree of fs has to be less than degree of g sub s. Okay, if that's the case, I can always write fs over gs as this form. So the only problem left, we have to figure out all these values. What are these values? What are those? Okay, now we'll talk about how to compute all those parameters, right? Okay, all right, we use example to compute parameters. So the first approach is what I mentioned previously in this example. You just have to, assuming you have some numbers a and b, or even c and d and e, that you do all the computation, you try to figure out what's the value that makes the numerator to be equal. Okay, so this is called a direct approach. So the first approach is where I just have to figure out write this form. Okay, try to try to figure out the common denominator, which is the same as the denominator I have for the original one, and I put together all the numerator. Okay. I just try to figure out, okay, what is the s? You should have something like this. You have coefficient for s squared plus coefficient for s plus a constant. So this one, it typically is a parameter of a1, a2, and a3. It's a linear function of that. This is also you have a1, a2, and a3. Similarly for this guy. Okay, so you just have to set this guy is equal to, let's say here is equal to 1. This guy equal to 2, and this guy equal to 1. Okay, you have 3 variables, linear function, you have 3 equations. Now you can figure out what is the a1, a2, a3. Okay, basically. Okay, now this one can be done, but it's a little bit complicated, right? Because especially I have what if I have multiple of this? It's very complicated to figure out these equations. Okay, now talk about a little bit simple way we can compute this. It's called the indirect approach. Okay, here's how we do it and why that's the case. Okay, assuming that here this is what we have. Okay, again, because according to the partial fraction decomposition, I can decompose this guy into this form. Okay, now let's see for a1, let's compute a1, right? If you want to compute a1, let's see I'm going to time both sides by s plus 1. Okay, both left hand side, right side by s plus 1. Okay, if you do that, I have a1 plus a2 divided by s plus 2 times s plus 1, and a3 divided by s plus 3 times s plus 1. Now here, because this will cancel out, you basically this will cancel out. So you have s squared plus 2s plus 1 divided by s plus 2 times s plus 3. You have this. Okay, the key trick we're going to play here is, what if I let s plus 1 to be 0? Okay, meaning I have s equal to negative 1. Now the main idea is I want to let this to be 0, this to be 0, so this will give me the actual value, right? This gives me a1, right? So if you do this one, you get a left hand side, you set s plus 1 to be 0, which means s equal to negative 1. The first one, it doesn't change because it's constant. The second one, because s plus 1 is 0, so this times 0 is 0. The third one is also 0. And of course, left hand side, you should also set s to be negative 1. So you have to divide the right hand side by setting s equal to negative 1. So if you do that, so I have s squared plus 2s plus 1 divided by, which is the same as this one, because this will cancel out. And we set it s is negative 1. So you put the s equal to negative 1 inside, you have negative 1 squared plus 2 times negative 1 plus 1 divided by negative 1 plus 2. You replace every s by negative 1, basically. Okay, negative 1. So this is value you have. So you can compute the final value, you a1, it would be 0. Okay. Similarly, you can do a2. a2, what the trick is, well, I just do time both. It's the same as you time the right side, the original one, by s plus 2. Okay. And then you value as s is equal to negative 2. Okay. And then you do the computation, you give negative 1. So similarly for a3, you do the same thing, and you get a3 is in the 2. So which means I have s plus 2. This here is given by 0 divided by s plus 1, negative 1 divided by s plus 2, and the 2 divided by s plus 3. Okay, this is eventually how you can decompose this complex form. Okay. Okay, the reason we can also do this one, you can also do some trick. You can also simplify this a little bit by doing this. Okay, but then for this one, you can also do the partial fraction decomposition, so which is just s plus 2, negative 1 plus s plus 3, negative 2. Okay, you can do the same thing. Okay. So once you have this, you have L inverse. The inverse Laplace. This guy is according to linear property I mentioned very beginning. So it's the inverse Laplace transform of individual components. Okay. And as a matter of fact, because this is individual component, this guy, according to the second property I mentioned over here, so I can put a constant number out, which means I can have put a negative 1 out, put a 2 outside. So the L, this guy, you can use a table actually to figure out very easily. Okay, this is, you can use a table. And as a matter of fact, you can also use this property to figure out, because the L of E minus lambda t is 1 plus s plus lambda, which also implies L inverse of 1 over s plus lambda is E minus lambda t. So here I have lambda is 2 basically, so this is E minus 2t. So I have negative 1 times E minus 2t. This guy is lambda is 3, right? So it's 2 plus 2 times E minus 3t. Okay, so this is how this is the way how I can find the inverse Laplace. So this is the partial fraction expansion can actually can simplify the computation quite a bit. Okay, so the key thing I want to emphasize over here is try to figure out the parameters, the a1, a2, a3. Of course, you can also, in general sense, if I have fs over g sub s, okay, assuming my g sub s is s plus lambda 1, s plus lambda 2, so on to s plus lambda n. Of course, I also assume the degree of fs is less than degree of g sub s. So I have here, this is given by a1 s plus lambda 1 plus a2 s plus lambda 2, so on and so forth, plus an s plus lambda n. And I'll talk about how it can be. So a1 or ai, any1, is given by fs g sub s times s plus lambda I. Okay, and you say s is minus lambda I. Okay, this is how it can be. This is hold true, lambda I. This holds true for I from 1 until n. So this is how to do decomposition. This is how you figure out each of the AIs and my L inverse of Fs G sub s is given by A1 e minus lambda 1t plus A2 e minus lambda 2t plus so on and so forth plus An e minus lambda nt. Okay, this is how we figure the inverse Laplace transform. For this form, when we have GS, when this guy has distinct and real poles. Okay.